Technology selection is one of the fundamental things that an architect does, and is a core component of system design. So technology selection essentially involves selecting a large number of components, out of which potentially the most important one is selection of a database. And that's what we're going to cover now. So database selection, right, is a very, very vast topic. So I've broken this into multiple lectures. And essentially in this lecture, what I'm going to cover is possibly the most common question that a lot of architects encounter, right? Which is essentially, what should you use for your primary database? Should you go for a SQL style database or a NoSQL database? So if you're not very clear on what is the difference between a SQL database and a NoSQL database, then at a very fundamental level, right, you have to look at a SQL database as a database that has relationships. So consider like a very simple example of a order and a customer. So consider that one of those tables is, this is a customer table and this is an order table. In a SQL database, you can link these two tables using some kind of a foreign key. So consider that in the order table, you have a field which essentially captures the customer ID. Using that, you can move from the order table to the customer table. And then you can also read some of the attributes of a customer like the email address, the phone number, and so on, if you want to essentially pass details about an order to a customer. So this relationship and traversing the using the relationships to traverse across tables is a very, very powerful concept, and that is what has made SQL databases very, very popular over the last many decades. NoSQL takes a fundamentally different approach and doesn't have relationships. So at a very, very coarse level, NoSQL, the core trade-off that they make is to not support joins. They're also like at a system level, the decisions to not to support ACID semantics and stuff like that. But at a very, very fundamental level, if you really want to understand the core difference, then essentially it is this distinction, right, of not supporting joins. Now, how can a database be popular because it doesn't support joins? So NoSQL has really picked up, and it is a bit weird that a database that says I have less functionality is actually becoming more popular. So what is the fundamental reason of not supporting joins in a NoSQL database, and what is the advantage of that? So the first thing that we will cover in this lecture is, why are joins bad? And and the primary reason here is that joins are compute intensive. So when you are actually going for joins, you require a lot of computation than as opposed to if you did not have joins. Now, of course, if you have a need to traverse two tables or traverse a relationship and you don't have joins, what do you do? So in a lot of NoSQL databases, what you end up doing is what's called denormalization, which is you will duplicate the data across tables, which is a crime in a SQL database, but is perfectly normal in a NoSQL database. So that's what we'll cover. The trade-off between paying the compute cost of joins or the storage cost of denormalization. Second thing that you have to really look at is the flexibility that joins gives you. And the way the joins work essentially means that it becomes very hard to essentially span your data across multiple servers. And that's the reason you will hear a lot about SQL databases don't scale and stuff like that. On the other hand, because the NoSQL databases have sacrifice joins, it is much easy to span your data across servers. So you can actually run your database across a cluster of servers as opposed to on one large server. And then the third important aspect is about auto scaling when your load increases. So because it's harder to move data across servers in a SQL database, you have to carefully scale up your databases when you need. On the other hand, on a NoSQL server, you can pretty much auto scale your entire workload. And as your workload increases, you can keep on adding more nodes, and all of that will seamlessly work. So this is the fundamental trade-off, right? Not supporting joins gives you a lot of benefits on the scalability, and that's something that what we're going to cover in detail now. So why are joins bad? First, you need to understand this very well, right? So assume there's a table on the left hand side, the table with elements in blue color A, B, and C. So let's assume this is, let's say, an order table. And then you have essentially a customer table on the right side, which has elements A, B, C, D, E. Now, if you want to join these two tables, right, you want to figure out the customer for these orders and stuff like that. What will you do? You got a record B. You need to find the record B on the right table, right? So you need to find your record B in this second table. Now this table has like elements A, B, C, D, E. So a very, very naive approach would be that you figure out, you compare B with all of these elements, and then you say, oh, I found B here. And then you essentially join B, and then you get a new record, which essentially has the relevant columns from this table and the relevant columns from this table, and then you output that record. It is very easy to understand that this essentially means that for every record here, you will actually do n comparisons, and you will end up with n square kind of a cost here. So of course, no one does this. This is just like a trivial, naive approach. What you can do is basically you can index this second table on this key in a way so that you can retrieve, you can figure out where B is in roughly logarithmic time. So you will use things like B tree and B plus tree and stuff like that. So you want to find a record B in the second table, you will go to the indexes and you will find it. And then you will do the same for C, you will do the same for A. And again, this is also not very cheap, right? This is also fairly expensive. You'll have to basically build indexes. You'll have to make sure that you do all these traversals for every record on the left side. Often what people do when they want to basically do joins, and this is essentially, this is like code inside the database. So what they do is they use the same idea that we use in this popular algorithm of merge sort. So if you sort two arrays and then you want to match elements, then you can do that in a much more simpler fashion. So for a moment, assume this is your table 1, this is your table 2. So if you find a record A, so you look at the top record, right, for both the tables. And then whichever is larger, that stays, and whichever is the smaller, you move to the next element. So in this case, both are same. So you say, oh, A and A have matched. Good. So let's create an output for A. B and B have matched. Again, very good. So let's do that. And then you move B further down, and then you say, oh, okay, B and B again match. So you have two records. And then let's have both of them move. So B, so this guy moves to D. This guy moves to C. Oh, C is less than D. They are not matching. And now look at this, right? If you have encountered C and you are already at D here, now you know very well that there's no chance that C can be present anywhere below this. So what do you say? Oh, C doesn't have a partner, so we'll skip C. And now we move on, right? So between C and D, C is less, so we will move to the next element, which is E. Now you'll compare D and E. R, so D is smaller, so D will never find a partner below E. So skip D. And then you move to E, and then you find E and E have matched, and then essentially you say, okay, this is also an element that I can join. Now this essentially means that you can do all of these comparisons across the two tables in order n time, right? Standard merge algorithm, right? It runs in order n. If you have two sorted arrays and you want to merge them, it takes order n. However, before you can do any of this, you will have to sort these. So if it's not already sorted, then you pay a cost of order n log n. So eventually you end up at a very, very similar place where in order to join two tables, you have to pay a fair amount of computation cost. Now, how do I do the same thing in a NoSQL table? So in a NoSQL table, if you want to do something like this, you will have to do denormalization. So before we go to denormalization, let's understand how your table is structured in a normalized fashion. So assume, I mean, in the same example, running example we have in the functional design course, right? Assume there's a course table with lots of rows, right? Hundreds of courses. Now the courses are categorized in basically based on category, right? So one category could be technology. There's another category called music. There's another category called recreation, and so on and so forth. So now you want to figure out, let's say, all courses for a certain category. So in a SQL based database where you support joins, what you can do is, so you'll basically do a join saying, give me all courses where category ID is such that category.name is equal to whatever I want. And this, what you also get a benefit that your category table has just 4 rows, and this data is not duplicated anywhere. All you have is basically just a key here, right? Category ID. Now, if you want to do something similar without joins, this is how you will do it. You will basically replicate all this entire table of 4 rows in every single course, right? So the name of the category and the description of the category will essentially be added to the course table, so that now you can say, okay, give me all courses with category name is equal to technology. Now, what has happened here, right? You have basically replicated what was only present for single time here into so many different rows. So essentially, now you'll have to read all of that data, and you increase the storage cost, and you increase the IO cost because you have to read all of that as well. But the benefit that you get is that you don't have to do a join anymore. So by letting go of normalization and duplicating some data, you have saved on joins. So you've saved on compute cost and you're paying storage cost. Now, why is this a good idea? And why were SQL databases very popular in the past? So so if you really want to understand this, you have to look at what has happened. If you look at decades of trend, right? The trend of how storage and compute costs have moved in the last 3 decades. So compute cost, right? We all know, right, that basically there is this power law which essentially says that compute cost has been decreasing every has been so the cost of compute has been reducing significantly every year, right? What has happened surprisingly, and something that is not as well known, is that storage cost has been decreasing even more rapidly. So the balance of where the compute cost and the storage cost was 3 decades back and where we are today, storage is a lot more cheaper than compute. And the trend of reducing storage cost is continuing, whereas the trend of reducing compute cost has slowed down a bit. And that is what really makes NoSQL a lot more appealing than what it was today. So clearly, right, you're paying a lot more in terms of duplicating the data. What you're saving is basically not paying for this expensive merges and sorts and stuff like that. And that's essentially the reason NoSQL is becoming so popular. So now let's look at what does join really give you in practice, right? How important are joins? So again, let's go back to the standard content marketplace where you have courses and you have students, and the students want to essentially look for courses that are relevant for them. So what's the most common query that you will make on your database, right? So we're looking at your primary database. So the most common query is that, oh, I want to know more details about this course. So get me details of course with ID equals 24. Now what kind of query is that? That's essentially a very simple query, like a key value query, right? The key is ID and then you essentially get details, right? So it's a very simple query, key value query, and uh, NoSQL databases will support it, right? Because it's all in one table and you're just querying based on a primary key. So everyone supports that. Now let's look at a slightly more complex query. Give me all courses with category equals technology, right? This is exactly what we're talking about. Now with some amount of denormalization, what we will end up doing is, again, in the course table, we will basically have the primary key as ID and then your secondary key, essentially. You will create a sort key, which is essentially based on technology. And then you can do this. So all of this can again be done in a NoSQL database. The second query, which is basically two entities, essentially going two tables. Now this is a little bit more complex on a NoSQL database, but there are a lot of concepts which you can use to create some kind of a hierarchy even in a NoSQL database, and you can put all of them in one table. So this is a simple query, which is a hierarchical query that a course has module has attributes. This kind of stuff can still be supported in a NoSQL database using some kind of a hierarchy notion. So for the moment, just assume that simple queries of two entity can still be supported on NoSQL. And then of course, simple updates, right? Update the course description, update this, single updates, all of those can be supported. Now, where joins really become powerful is basically when you have more complex queries. So look at this query, right? I want to know all courses that essentially have the same instructor as this one, essentially me. And then you also want to figure out they have been enrolled by students who are friends of Jason Lee. So let's say Jason Lee is some student who's looking at this course and says, oh, I want to look at more courses. And the platform gives some recommendation basically, and the recommendation is, okay, if there is another course by Akshat Verma, it should be relevant. And then whoever are friends of Jason Lee, by that friend definition, whatever it is, then those courses should be relevant as well. So you use that as a filter criteria. Now look at this one carefully, right? It needs to join an entity called course with an entity called enrollments with an entity called student to student relationship. So we have to join these three different entities in a complex fashion, and that is something that you will actually end up jumping through a lot of hoops if you want to do it in NoSQL. If you want to do this in a SQL, it's a very simple join. You can go ahead and do this. Now that is the power of SQL, right? Something as complex, something you figured out much later, you can actually do this. And similarly, right, if you want to do multi-step transactions, you have a transaction which writes in three different tables, you can do that very simply in SQL. In a NoSQL, even if they support it, it's actually going to be fundamentally very complex for them to support it. And it will come at the cost of some of the good things NoSQL has. So if you actually have a lot of requirements of the red color, then you better use the flexibility of SQL, and that's essentially what I'm trying to communicate in this slide. So now this complexity of join, right? What exactly does a SQL server have to sacrifice to do that? Now, this is again a very, very fundamental aspect of where SQL servers start to saturate in terms of scale. So a SQL server fundamentally, right, because it needs to look at two different entities and join them using some key, it needs to bring them together. So assume that you had a SQL that essentially had data spread across two servers in some random fashion. So here is a table in blue, ABC, with the records ABC, and you have another table in green with records ABCDE. But as luck would have it, BCD are in server 2, whereas A and E are on server 1. Now look at how your join technique will work. Assume you only join within a server. What will happen? You will join A with A, very nice. A gets outputted. And then you will look at B and E. What will you do now? You will realize, oh, I have come to B, so B, I will never find a partner, so drop B. Then you will look at C, O, and then C and E. Oh, again, C is less than E, so let's move on. I will never find a partner for C, drop C. Whereas, if you had looked at the other server also, you'd realized B does have a partner in the second table, and C also has a partner. So if you want to not make that mistake, what will you have to do? You will have to actually copy all of these records on the same server. Now, if you copy all of those records also on the same server, before you do the join, net, you're doing the join on a single server, which essentially means that you are limited by the capacity of this single server. So it's very, very hard for you now to distribute a computation, distribute a join across servers. And that is where the scalability limitation comes fundamentally for a SQL server. On the other hand, right, because you sacrifice joins, in a NoSQL database, you can actually use a large number of servers and spread your data around in a very, very seamless fashion. So look at basically same thing, right? You want to figure out some customers and some orders, and the order actually has the customer details also, right? So you have the order table spread across all of these. Look at your query. Your query is, I want to find, let's say, all orders for customer X. I can run this query on all of these 9 partitions. All of this will give me some orders for that customer, and I can just join them together here. And this is not join, sorry. So I can just merge them. I can just group them together. And then you essentially get the response. I never actually have to move raw data from one partition to another data partition, because see, what is your, you have one table you will basically partition that table based on some key across all of these guys, and the computation will be performed in parallel in a distributed fashion across all of them. So you're no longer limited by the compute capacity of a single server. And then all of them will generate their result, and then you essentially combine all the result and send it over. So it's so simple. So basically you can run your computation across servers in a very, very simple fashion. And that is the benefit you get because you did not have joins. If you had joins, then the second table could have data anyway. And then we'll have to bring that table to the same place. So that is the basic advantage you get if you choose to sacrifice joins. So how do people actually scale SQL databases, right? There has to be some way or the other. So one simple way, right? If you have scaling challenges only on the read side, then there's still a very fairly simple technique, which is essentially a master slave technique. So you have a master database from which all changes flow to slaves, and then your reads will essentially happen on slaves. Now, of course, do see challenges a bit in terms of reads sometimes falling behind whenever there's a lot of load on the master. But okay, those are simple things, and if you look at an eventually consistent model, we can still live with it. So reads, it's still okay to scale them. But what if you want to scale writes as well? In that case, what you end up doing is what is called sharding. So what exactly is sharding? So look at let's take the example of the customers and orders, right? So I have a very, very large order table, and there's absolutely no way a single server can actually process uh, that particular table, right? You cannot do a join on that table in one server. So what do? You essentially change your application and say they will actually write to different servers. So, and the way they will write is that you will do some kind of a sharding. A very common sharding that you can do in this case is to say all the orders from USA will go to server A. All the orders from Europe will go to server B. All the orders from Asia will go to server C. Now, what does that mean? That means that your applications are now aware of which request is coming from which region, and then they are redirecting that request to the right database server. The benefit that you have is that all relevant data for US customers is in this particular server. So the customers are also here, their orders are also here, and you can actually join them. So you are no longer limited by the capacity of one server. You can use these servers because you've split your database logically into different shards. Now, of course, this essentially means your application has to be aware. And this also means that you have to be very, very careful in when you do sharding. And whenever you do sharding, you'll have to actually plan this very well. And that's exactly the challenge that we have, right, in terms of scaling a SQL server. On the other hand, on a NoSQL server, right, you were running some workload and then you became more popular and now you want to essentially scale up more. So your current set of servers are not enough. In a NoSQL server, essentially most of the techniques are centered around what is called consistent hashing. What exactly is a consistent hashing, right? So in a consistent hashing, you have a ring and you have every key basically will create a hash number, and that hash value will map to that hash value will be mapped to some part of this ring. And what you're pretty much going to do is saying all hash values that map in this range will be stored in B. And if case you want to have replicas, then they will be stored in B and replicas will be stored in C and D. Now, why is this very useful? Assume that you now have more load and you need to add one more server. What do you need to do? You will essentially need to break this hash range, right? This ring from, so introduce another element, right? So introduce an H here and then redistribute the hash ranges, and you can now serve the same workload without any change on the application. By the way, consistent hashing also has some issues, and it is never used exactly like this in practice. Now, the issue there is that once you add one more node and it needs to look at some range, then the range for all of these guys also changes, and this reorganization may take a little bit of effort because a certain amount of data copying will happen. All of this will happen transparently, but a lot of serverless NoSQL databases, they have more advanced techniques built on top of consistent hashing to minimize the data transfer. So when you add a new server or remove a server, there is pretty much no impact on performance. The basic idea there is to actually use another level called a virtual node, which maintains tokens of the ring. And then when you add a new node, only some tokens get redistributed. So the amount of data that moves is equal to the amount of capacity that one node will have. And if you have a large number of nodes, then it is a very, very small percentage. So in case you do not understand a lot of what I'm talking about consistent hashing, the summary that you should take here is that in a NoSQL database, you can basically introduce another server, give it some part of the data. All of this can happen seamlessly without the application even knowing about it. There will be a small amount of data copy, but that data copy is such a small percentage that it will not lead to performance impact. And this is one fundamental notion that differentiates NoSQL servers from typical SQL servers. There are also some distributed SQL servers that have come in, like Spanner and all, that try to do all of this in a very sophisticated fashion. But the run-of-the-mill SQL servers versus the run-of-the-mill NoSQL servers, the way you can introduce new nodes to horizontally scale as your workload increases is one fundamental difference. And all of this can happen because all your computation can run on one server. So, uh, and, and you don't have to actually do distributed joins. So net, right? What I want to do is end this lecture with the basic summary of SQL versus NoSQL, right? Because a NoSQL server sacrifices joins, it saves on the compute cost of joins by paying for extra storage cost. And it is also able to easily run across a cluster of servers as opposed to a single server, a single large server that a SQL server would run. And it is also easy to scale up a NoSQL server by adding additional nodes. So these are the big benefits of a NoSQL server. The big benefit of a SQL server is the flexibility that joins give you. If your application has some kind of complex queries, it can still support it. And that fundamental distinction is what you need to keep in mind while picking your primary database, whether you go for a SQL or a NoSQL. And we will actually cover that and have very good rules of thumbs on how to do this in the subsequent lectures.